So last class we took derivatives of inverse trig functions. This class we're going to be taking integrals of inverse trig functions and working backwards. Immediately when we're looking at these formulas though, you're going to notice that there are a's in spots where there were ones. Don't be freaked out by that. The formulas still follow the same pattern. So when I see the square root of a squared minus u squared, that's going to be arc sine of u over a plus c. Now remember, in this instance, a is a number and u is the variable. I could write that same as sine inverse of u over a plus c. I do think it's good to know both versions of these. When I say both versions, it's not really both versions, but arc sine versus sine inverse. When I see u squared plus a squared, just like when I saw 1 plus a squared, that was tangent, but there's a catch here. We're going to throw a 1 over a in front of this. So 1 over a arc tangent u over a plus c. Remember, alternatively, I could write 1 over a tan inverse of u over a plus c. Last but not least, when I see the u square root of u squared minus a squared, even though that's not a 1 where that a squared is, this is still secant. I would also like to point out you're not going to see the absolute value bars here because they were assumed that it's already positive. Remember that these two things, whatever they are right here, they must match. So whatever your variable is right there must match. So when we see something like this, that's going to be 1 over a arc secant absolute value of u over a plus c, and remember we could write that as 1 over a secant inverse absolute value of u over a plus c. So let's dive right into an example. Let's dive right on in. So immediately when I see this first example here, I notice that it follows a pattern of number that's a perfect square minus a variable that's a perfect square. And so immediately my eyes go here, and thinking backwards, this must be arc sine. When I do these sorts of inverse trig integrals, I do like to identify what my a is and identify what my u is so that I can also identify what my du is. And you must be careful here. So it's kind of like a u substitution. So the number that is being squared is 2. The variable that is being squared is x, which is going to make du just dx. So if I were to rewrite this, which you don't have to, I could say this is du over the square root of a squared minus u squared. Notice it follows the pattern of arc sine, which will give me arc sine of u over a plus c, and we can substitute back in our u and our a plus c. Now, do I have to rewrite it with the u's and a's? No, you don't. You don't have to rewrite it that way, but it is good to make sure and to see all the pieces kind of come together. When I look at example 1b, we can see that it follows the arctan pattern. It is a definite integral. So in this case, my a value, the number that's being squared, would be 3, and my variable that's being squared is x, which would make du be dx. So if I were to take the integral of this, you could rewrite it. I'm not going to rewrite it. It would just be 1 over a arc tan of x over 3 evaluated from root 3 to 3. You are going to have to know your unit circle here, so be very careful. I would put the 1/3 on the outside. So now I have arc tangent of 3 over 3 minus arc tangent of root 3 over 3. Keep in mind where arc tangent is defined. So if I want to find arc tangent of 1, that's going to say where on the unit circle is tangent 1. Well, that would be at pi over 4. And the arc tangent of root 3 over 3, where on the unit circle is tangent root 3 over 3, and that would give me pi over 6. Distributing this 1/3 in, I would have pi 12ths minus pi 18ths. Finding a common denominator, perhaps 36 in this instant. Multiplying by 3 in the numerator, multiplying by 2 in the numerator to give us a final answer of pi over 36. And just while we're following the pattern here and doing kind of one of each kind, this last one here, 1c, is following our arcsecant pattern. So notice I've got my variable squared, and then I have an a squared. So let's identify all of our pieces. My number that's being squared in this case will be 5. My variable that is being squared is x, which will make du just dx. There's a method behind, or a reason behind why I am putting my du, and that'll come up in just a little bit. So notice if I were to rewrite this, which again, you do not have to rewrite this would become du over u root u squared minus a squared. Okay, again, you don't have to rewrite it, which would give us 1 over a arc secant absolute value of u over a plus c. You're going to forget that absolute value, and it's going to become important, so don't forget that piece of your formula. Substituting things in, I've got 1/5 arc secant absolute value of x over 5 plus c. Okay, so let's get to some little bit zestier examples. And we get to some things like these. Now, the juxtaposition of these 3 examples is actually important. Notice that these 3 examples look very, very similar. And immediately, I want you to be able to see the difference in these 3 examples. And it has to do with the numerator. So notice this one has a numerator of 4. This one has a numerator of 4x, and this one has a numerator of 4x squared. And I've put these side by side because as you guys are learning to diagnose problems, these are all very different problems. So looking at 2a, I would probably take that 4 and park it on the outside. Immediately, I can see that this follows the arctan pattern, where a would be 3, the number being squared, and u is going to be x. That will make my du just dx. You don't have to rewrite this, so we're going to go right for it. I'm going to keep my 4, and then remember that arctan has a 1 over a arc tan u over a plus c. That'll give me a final answer of 4/3 arctangent of x over 3 plus c. So this first one was inverse trig, but the second one is not inverse trig. In fact, the second one is plain old u substitution, where u is x squared plus 9, and our du is 2x dx. Notice I don't have that 2. I have a 4 there, so let's multiply both sides by 2. So 2 du is going to be equal to 4x dx. So I can rewrite this now as 2 integral, my 4x dx is going to become 2 du, and my denominator is u. Well, guys, this is just a log. 2 natural log absolute value of u plus c to give me a final answer of 2 natural log of x squared plus 9 plus c. Now, the spiciest one of all 3 of these would be 2c. And so it's not inverse trig. I can't u sub it away, so u sub won't work. So remembering tools we have in our toolbox, let's divide. Now, unfortunately, you cannot use synthetic division here because my divisor is quadratic. So we're going to do long division, guys. Remember that when you're doing long division, I want you to set up placeholders for missing terms. Okay? Now the question you're going to ask yourself is, x squared times what gives you 4x squared? The answer to that is going to be 4. We multiply by each one of the terms. 4 times x squared is 4x squared. 4 times 0x will be 0x. And 4 times 9 gives me 36. Just like a normal division problem, we subtract. If I subtract, my 4x's are gone, my zeros are gone, and 0 minus 36 will leave me a remainder of negative 36. So where do we go from here? We're going to take this thing over here, and we're going to rewrite this as the integral of 4 minus 36 over x squared plus 9 dx. Now, as you're probably already suspecting, we're going to split this thing up. I'm going to split it up into 4 dx. Let's take the 36 to the outside and 1 over x squared plus 9 dx. I hope you see it. I hope you see the cow right here, because this guy right here is inverse trig. Our a value is 3. Our u value is x, which makes our du dx. So going term by term, the integral of 4 dx will give us 4x. We're going to bring down our 36. And then I have an arc tangent integral here, where I'm going to go 1 over a arc tangent x over 3 plus c. For a final answer of 4x, 36 divided by 3 will give me 12 arc tangent of x over 3 plus c. So the key to this question, it was an inverse trig, but I had to do division in order to execute it and make it happen. Okay? Now, sometimes it's not going to be so simple as du being just dx, and there's a method behind my madness as to why I've been writing that. So if I look at example 3a, it becomes pretty easy to see that the number being squared here is 2. But when I look at the second piece, there is a number and a variable. So the number being squared with the variable is 5x. So our u is 5x, which makes du 5 dx. Dividing by 5, I'm now going to rewrite this thing. So I'm going to need a 1/5 integral, du ends up on the top, square root a squared minus u squared. So it is an inverse trig, but I had to add in an extra 1/5, and it's really easy to miss that 1/5 if you're not paying attention. So pay attention. When I take the integral of this, it's my arc sine, so I'm going to get 1/5 arc sine of a over, u over a plus c. Now, something that's interesting, and I hope you caught this, arc sine is the only one that doesn't start with a 1 over a. If you go back and look at your formulas, notice that arc tangent has a 1 over a, and arc secant has a 1 over a, but arc sine does not. So let's do another one, kind of spicy example like this. This is still going to be an inverse trig. But check it out. The x in the numerator isn't super obvious. I think the number being squared here would be 9. My u is going to be 8x squared. Now watch what happens when I du this. I get 16 dx. Ooh, 16. Come on, Lowry, get it together. 16x dx. Notice there's your x, there's your dx. Get rid of the 16, and now we see where that x dx is going. So I'm going to churn out a 1/16. X dx becomes, that x dx became 1/16 du And then in my denominator, I have 1 over a squared plus u squared. So this is an arctangent. The 1/16 stays as a constant. Remember that your rule is 1 over a arc tangent u over a plus c. Let's fill in all of the pieces. So I've got 1/16, 1 over a arc tangent u over a plus c. Let's go ahead and multiply that 1/16 and the 1/9 to give us 1/144th arc tan of 8x squared over 9 plus c. So we're getting into some zestier examples. Speaking of zesty examples, let's look at 3c. Now, if I was diagnosing this on the AP exam, immediately I'm noticing u sub isn't going to work because I do not have a 2x. And it doesn't look like an inverse trig, but it is. So let's recall a skill from both Algebra 1 and Algebra 2. So in Algebra 1 and Algebra 2, we did something called completing the square. So we're going to leave this x squared minus 4x here. And I'm going to shove the plus 7 down the line. And I'm going to create a blank for a new number here and a new number here. And I'll explain why there's two blanks in a minute. To find the number that goes in the blank, you take your b value and you're going to cut it in half and square it. So 4 cut in half is 2. 2 squared is 4. So if I'm going to put a 4 here, I can't just willy-nilly add a 4. I need to balance that 4 out by making this one a negative 4. So in essence, I'm adding 0. Okay? If I factor this, I get x minus 2 squared. 7 minus 4 is 3. So watch what I just did. If I rewrite this, I have dx over x minus 2 squared plus 3. Again, not super obvious that this is arctangent, but it is. The number that is being squared to get 3 is going to be root 3. The u is going to be x minus 2 because it's being squared, which makes du just dx. So this big gross thing is really just the integral of du over u squared plus a squared. It's arctangent, which means the integral of this thing is 1 over a arc tangent u over a plus c, filling in all of the pieces, 1 over rad 3 arc tangent x minus 2 over rad 3 plus c. Now you're going to be tempted to want to rationalize that. Don't rationalize it. You're just wasting your time. You're absolutely just wasting your time. So last one, actually not last one, but we're going to do a couple more together, and then I'm going to let you guys do some review. Let's look at one like this. So again, not obvious what's going on here. I can't u sub it. So we're going to do something interesting. We're still going to complete the square, but we're going to do it just a little bit spicier. You cannot complete the square with this negative out in front, so you need to factor out the negative. That will change the sign of my 6x. Let's bring in a new spot here, and let's put a new spot here. Remember that the two numbers and those blanks must balance out. So again, we're going to take our b value. We're going to cut it in half, and we're going to square it. Negative 6 divided by 2 will be 3. 3 squared is 9. But this number 9 isn't really a 9. It's actually a negative 9. By the time I distribute that negative in, that's really a negative 9, which means to balance it out, this must be a positive 9 in order to look like it's adding 0. So whatever you do right here, the two numbers in these blanks must actually balance each other out. And even though that looks like I'm doing positive 9 in both instances, it's really a negative 9, okay? Factoring this, I'm going to get x minus 3 squared plus 9. So let's rewrite our problem. I now have the integral of 1 over the square root 9 minus x minus 3 squared. If I make a 3 and I make u x minus 3, which will make du dx, I forgot my dx. I've got du over the square root of a squared minus u squared. Guys, this is just arc sine. So it wasn't a super obvious arc sine from the beginning, but it ends up being arc sine. So remember, arc sine does not have a 1 over a in the front of it, so it's just going to be arc sine u over a plus c. Substituting in that u and that a, I get arc sine of x minus 3 over 3 plus c. Okay? Now, I've put 3 problems side by side here, and these next 3 problems are going to be some spicy, spicy, spicy examples. So these 3 are going to be where I finish us out. Spicy, spicy. Okay? So I put these 3 on here because they require a little bit of manipulation to begin with. So let's look at 3e. If I u sub it, u sub isn't going to work. So what do I do? Well, let's split it up. Let's keep our x over the radical of 4 minus x squared dx. And then let's take the 2 to the outside and keep that as 1 over the radical of 4 minus x squared dx. Now there is strategy here in doing so. The reason I have split these up is because I'm going to argue that this thing right here is going to just be a plain old u sub, where u is 4 minus x squared, and du ends up being negative 2x dx. Getting rid of the negative 2, I can rewrite this integral as negative 1/2 integral 1 over radical u du. And that ends up not being so bad. And then this guy over here ends up being an inverse trig, where a is 2 and u is x, making du just dx. So this becomes 2 integral 1 over square root a squared minus u squared du. If I'm thinking through this and using power rule, just treat this like u to the negative 1/2, if that helps your brain kind of process through that. So taking our antiderivative, I'm going to have a negative 1/2. I'm going to add a power. I'm going to divide by that same power. On the right-hand side, this is an inverse sine, so 2 arc sine u over a, and we only need 1 plus c in this. So really our final step, and I caution you here, realistically, if we're going to use both u's on both of these integrals, it's not super best practice here, but for the AP exam, this will work, okay? So negative 1/2 multiplying by 2, I'm just going to end up with a negative because those things are going to end up reducing away. I'm going to bring my 4 minus x squared back to the party, to the 1/2 power. And continuing on, I've got 2 arc sine of x over 2 plus c. So that ends up not being so super gross. Let's get a little grosser, okay? So I look at something like this and immediately my brain goes, ooh, u substitution, but not quite. If I do try and u sub this, I get x squared plus 8x plus 25. If I take the derivative of this, I get 2x plus 8 dx. I have a 2x plus 5, but not a 2x plus 8. So we're going to do some voodoo. It's not really voodoo. It's actually mathematically legal, but go with me here. I want to keep 5. So is there a way I can keep 5 but turn it into an 8 and something else? So I'm going to keep this 2x here, and I'm going to keep this x squared plus 8x plus 25 here. And instead of 5, I'm going to write plus 8 minus 3. Now, I'm going to argue that is still 5. All I've done is expand this out. So why did I do this? What gain does this give us? Because what I'm going to now do is I'm going to chunk this into 2 pieces. I'm going to keep the 2x plus 8 over this x squared plus 8x plus 25. And then I'm going to go over here and call this 3 and 1 over x squared plus 8x plus 25 dx. Now what that just does for me is it allows me to u sub this one. So the left-hand integral folds up really nicely into du over u. But what about the right-hand integral? That is not so pretty until you complete the square. So we're going to go over here and take that x squared plus 8x. We'll bring a new number to the party, plus 25. 8 cut in half would be 4, and 4 squared would be 16. So I'm going to put a positive 16 here and a negative 16 here, which if I factor that, will become x plus 4 squared, and 25 minus 16 will give me 9. So this integral becomes 3 integral 1 over x plus 4 squared plus 9 dx. We already know that this integral of du over u is going to produce a natural log, absolute value of u. I should probably make this a little bit more obvious what's going on here, but ultimately this thing is really just if a is 3 and u is x plus 4, then du is just dx, and so this thing is really u squared plus a squared, also known as arctangent. And let me change that to a du. Okay. So substituting this back in, I've got the natural log, the absolute value of that big long x squared plus 8x plus 25. And I know that this piece is going to churn out an arctangent. Remember that an arctangent has 1 over a arctangent u over a, and let's throw a plus c for the good of the group and the whole thing. You can reduce away those 3's, which makes kind of a pretty answer, and I'm not going to write the final answer with those 3's gone, but you get the idea. Okay. Last but not least, one final spicy example. Okay. You have not seen one where you have an arc cosine in the integral, but I'm going to argue we're going to do something a little bit interesting. Do you guys see that denominator? That denominator isn't really a denominator. I'm going to write it like this. Maybe some light bulbs will go off. We're going to do u substitution. And we're going to let u be arc cosine. And based on the derivative rules that you learned the other day, the derivative of arc cosine, which I hope you know, is negative 1 over square root 1 minus x squared dx. Notice that's exactly what you have right here with the exception of the negative. So let's get rid of the negative. 1 over radical 1 minus x squared dx. So that when I rewrite this, I have negative u du. This thing just turned into negative u du. Holy cow, super easy. I do want to change bounds. So let's change bounds. If I plug in 0, the arc cosine of 0 is going to be pi halves. If I plug in root 2 over 2, the arc cosine of root 2 over 2 is going to be pi over 4. It's going to make this integral really easy because I've got negative u squared over 2 evaluated from pi over 2 to pi over 4. Subbing this in, let's keep the negative on the outside temporarily. I'm going to get pi over 4 squared, and remember that's still divided by 2, minus pi halves squared over 2. It doesn't matter that these bounds are technically in backwards order. It'll churn out the negative anyway, so try not to be freaked out about the fact that we're going from pi halves to pi over 4, okay? I'm going to end up with pi squared. 4 squared is 16. 16 divided by 2 is going to give me 32. And then I've got pi squared. 2 squared is 4. 4 divided by 2 is going to give me 8. And I've got negative pi squared over 32 plus pi squared over 8. Let's common denominator it. So let's multiply by 4, multiply by 4 for negative pi squared over 32 plus 4 pi squared over 32 for a final answer of 3 pi squareds over 32. So now here's the challenge, okay? I've basically built in nothing but review on these last few pages. And so everything from here down is review, and you are going to be expected to finish it for today's lesson. So you're going to get all the way through right here to 4F, and you're going to do 1, 2, 3, 4, 5, 6 review problems independently.